The main topics covered in this video that go along with your reading will be initially covalent bonds, hopefully a little bit of review, carbon compounds that we call alkanes, how to look at flat structures of molecules on paper or on screen, how to relate those to three-dimensional structures, and then looking at the properties like how they can rotate, and finally a key concept of isomers. So, briefly reviewing, what does a carbon atom look like? If you recall from general chemistry, we have the nucleus of the carbon atom here, and the positive protons are shown in green, the neutral neutrons are shown in white, and orbiting that nucleus are the red electrons. You have inner electrons that don't get too involved in bonding. So it's almost as if this whole inner part is just a spectator of everything. The orbiting four outer electrons that we call valence electrons are the ones that form bonds. And so this helps explain why carbon forms four bonds. It can form different types of bonds. As we'll see later, in this video, we're just going to look at carbon forming single bonds, but it can form double bonds and triple bonds too. So as you see here on the right, carbon forms four bonds. Let's say it forms bonds to hydrogen. Well, a hydrogen atom is a proton, if I do the green like in the video, or in the structure on the left, that's a proton in the center of the hydrogen atom with an electron orbiting. That's all a hydrogen atom is, a proton and an electron. So if we have four hydrogens bonding to a central carbon, each hydrogen donates an electron to the bond, like these right here. The carbon then, as we see on the left, contributes four electrons, one for each of the bonds. Each of these bonds is a covalent bond, which is defined as shared pairs of electrons. Very important to remember that. So look at what we're looking at here. The C really stands for this central part here that I'm circling, doesn't it? And then the bonds are straight lines, each of which has one of the electrons from carbon and one from each of the hydrogens. The H symbol, drawn here like that, represents basically just a proton. Okay? So this is already an abstraction, right? It's an abstract symbolism for the molecule. Let's make it a little bit more now. In place of each of those hydrogens, let's put a CH3 group. So now each covalent bond is between carbons, where each carbon is contributing an electron to those covalent bonds. So don't forget that each line is a representation of two electrons being shared. Of course, each of these outer carbons is sharing three more electrons with three hydrogens, just like we saw above. It's really important to get comfortable with different ways of drawing compounds. So drawing this compound, which happens to be called neopentane, we'll get into naming later, this compound takes a really long time to draw. It does show everything in detail, but even this abstraction can be further abstracted for speed, and in fact it does help in some understanding too, because this structure is a little bit too much to look at. So we can abbreviate this structure as this one right here. Notice I just condensed each group of CH3s as CH3. And this structure can be even further condensed as just a line structure. And your book calls it a condensed structure, I believe. So compared to drawing this first structure, this structure takes seconds. And it also eliminates the distraction of looking at all those hydrogens, in fact. So there's more to it than this. Okay, now these later two ones, for example, don't really look like this. This is their flat structures on paper. They're two-dimensional structures. Let's take a look here at what it really looks like, well, in 3 dimensions. Notice the central carbon doesn't have any hydrogens on it, just like we saw above. This is a much more accurate picture, and this is what you should get for any of the molecules we're working with when you buy your model kits. See how much more information this shows. Look at the angles and the depth. All right, so there are ways to draw this showing something that looks much more three-dimensional on two-dimensional paper, and that's this structure right here, where you have what I call the wedge and the hash marks. And the wedge is coming toward us, and the hash marks are away from us. That's a really nifty way to show this, isn't it? So these two here and these two here are in plane. The one CH3 coming toward us and the CH3 going away from us is represented right here. And then to further condense it, you could draw like that. So we have a very important key concept of implied atoms that I'm circling here. So notice in this structure here, we have an implied carbon in the middle, an implied carbon on each end of each line, very important, and then implied hydrogens on each carbon. You can do that for all of them. Implied atoms. It's really important to get very fluent with this. This chapter 12 is one of our more important, maybe the most important chapter, because if you get off on the wrong foot in this chapter, you're in trouble. You need to be able to recognize where implied atoms are, say, in a structure like this. And to be able to go from one structure to the other quickly. Here's another example. We have a structure with 4 carbons, and how did I know how many hydrogens to add to each carbon? I just remembered that each carbon can only form 4 bonds. So the carbon on the end has 1 bond there. That means it needs 3 hydrogens to complete 4 bonds. This carbon right here is bonded to 2 other carbons, so it needs 2 hydrogens to fill out its 4 bonds. So the condensed structure of that is this, right? Implied carbon, implied carbon, implied carbon, implied carbon, and then filling in all its full complement of hydrogens which are implied in this structure. Now, any single bond can have rotation around it. So here's the same molecule shown in a more three-dimensional way. And in fact, I could have put, for example, up here, I could have put a wedge and hash marks on each of these ones, like these ones here too, to show something that looks a little bit more like what you see on the bottom. Notice it's got rotation arrows shown here, here, here. That's indicating that all of these single bonds have free rotation around them. Notice if we just take this rotation here in the middle, we can rotate it to get to this structure. Okay? And then there's another concept that we'll explore further throughout the quarter. In this structure on the end, where it's rotated into this conformation, these methyl groups, I'm calling them methyl groups because that's what they are. We're going to get to that in nomenclature. These get very close. So this is preferred. I think I spelled that wrong. And lower because it's lower in energy. And it's lower in energy because this is higher in energy due to these getting a little bit too close to each other and repelling. There's a repulsion. So the preferred energy is where they're furthest apart. Okay, another key concept, isomers. The definition of isomers, concepts with the same molecular formula but different structures. So the molecular formula, say C5H12, that's what we mean by a molecular formula, excuse me. We can draw a molecule that has that molecular formula by starting out this way and just connecting 5 carbons like this. And notice I make it sort of like zigzag because that's the way they look more in real life, like the structure is up here. And then you can fill in all the hydrogens and convince yourself that it has 12. Look how long this takes, though. I can draw a condensed structure so much more quickly, right? Now, if I take, say, this CH3 group here, which would be this right here, and detach it and switch it and move it over to here, for example. So I'm detaching that CH3 group and then reattaching it there. I'm actually detaching one of these hydrogens in order to do that, right? So I'm actually detaching and switching this with this. So I'm breaking bonds and switching two things and then reattaching them to get this. This has the same molecular formula, C5H12. And you can convince yourself of that by filling in all the implied carbons and hydrogens. If you have to detach and switch atoms, if you have to break bonds, detach them by breaking them, switch them and reattach them, you're definitely dealing with different molecules, different structures. So not a rotation, not a conformation, but a different molecule entirely. So isomers are different molecules because you would need to detach and switch and reattach bonds or groups of atoms. That's a pretty good reality check that you have an isomer if you have to do that to get from one to the other. There's one other isomer with this same molecular formula, and it's this one, which happens to be the molecule I was rotating around above. So this is just revisiting what we saw above. If you have a molecule like this and rotate around that central single bond, you get this molecule. So these are conformations, achieved through rotation, not isomers. So if you have an exercise, which you have many assigned, asking you to draw isomers of this molecule, for example, this is not an isomer of that. It's just a rotation. So these are the same molecule. Okay, and that's the end of video once a